Good afternoon, everyone, and thanks for joining this presentation. My name is Avani, and I'm working as a project development and strategy manager at Wärtsilä Energy in Singapore. So today I'll be talking about how we can decarbonize the power sector with sustainable fuels, and in particular, what the prospects for hydrogen-based generation are. So before we jump into the topic, I wanted to briefly share about a little bit about what Wärtsilä Energy does. So at Wärtsilä, our vision is a 100% renewable energy future, and we see our role in enabling the energy transition by providing the technologies and the services that are needed to make this happen. So our whole belief is that as countries are adding more renewables into their power system, there will be a crucial need for system flexibility. And this flexibility can come in the form of technologies like gas engines, and also battery storage, along with life cycle services to bring in the whole end-to-end element. So just to give you a sense, we have a global presence with over 75 gigawatts of installed capacity of engine power plants globally, and about 5 gigawatts of energy storage systems installed globally. And as you can see here, the Asia Pacific region is one where we have a very large installed base, which makes this region quite a key market for us. All right, so jumping into the topic today, we all know that thermal generation has evolved significantly over time. As you can see, 40 to 50 years ago, diesel oils and heavy fuel oils were the norm, and then natural gas quickly became the front runner in fuels. And today, we still believe that there's room for all fuels to play a role. We're still seeing sort of on remote islands and such where gas isn't available. People are still running on traditional liquid fuels. There are countries which are moving more towards LNG and gas. But then as we look at decarbonization, it's also important to consider those clean and sustainable fuels like methanol, ammonia, and of course, hydrogen. So the whole point of this presentation and the question that we all want an answer to, or at least I definitely do, is hydrogen-based power generation just a buzz in APAC? We're continuously hearing about hydrogen and announcements being made and MOUs being signed, but really, what are the fundamentals behind hydrogen? So if you look at this graph from Bloomberg New Energy Finance, you can see the forecasted electricity generation mix by technology and fuel in APAC from now until 2050. So what you see here in gray is the share of coal and natural gas starts to decline and eventually phase out. Solar there in yellow and wind in blue grow massively. Now, what's not very visible in this chart actually is hydrogen. In fact, it's so small that you can really barely see it. It's that purple color right in between nuclear in red, and then basically CCGT in blue. So why is that the case? If we're talking so much about it, why are we not really seeing it in these forecasts? And what can we do to make a greater push for hydrogen in our power systems? So while there are many moving parts to make hydrogen-based power generation a reality today, let's try to break it down and simplify it into three fundamental puzzle pieces. So I like to call this the hydrogen trilemma. So first, obviously, you need the supply of hydrogen. And here, I'm not only talking about the availability of the molecules, but also at what cost are you able to secure hydrogen supply. Secondly, you need to have the midstream infrastructure in place. So whether the transportation is being done through pipeline, trucks, or ships, and then storage is a whole other challenge, which we'll discuss a little bit later. And last, but certainly not the least, if you somehow manage to get the supply and the infrastructure in place, you, of course, need the power generation technology to be able to run on hydrogen. And if this wasn't complicated enough, all of this does still need to be underpinned by policies and grants. investments and the understanding that hydrogen will act as a balancing fuel and not as a baseload fuel. So a really good example not too far away from us in Southeast Asia in terms of policies is in Japan, where there is this targeted existing capacity mechanism for up to 30% volume of hydrogen. We also see state-owned utilities in Australia providing funding for hydrogen projects, like in Queensland. The utility there is actually funding a 400 megawatt hydrogen-ready peaking power station with a 35% hydrogen blend. And of course, on the third point, because of the cost and the logistics of hydrogen, as we'll see a little bit later, we also need to have the common understanding that hydrogen power plants will not run as baseload, simply because the economics do not make sense, and it's probably not the best use of the hydrogen molecules. So let's take a look at each of these 3 points in the hydrogen trilemma one at a time, starting with the supply side. So where will, or maybe where should, green hydrogen be used to begin with? So the primary use of hydrogen molecules will be prioritized towards the industrial hard-to-abate sectors, such as steel, aviation, shipping, and chemicals. And in most cases, these industries won't actually use the hydrogen directly, but they'll use chemicals built from hydrogen. So as you can see from this graph, the use of hydrogen in the power sector is in blue, which is just that small portion towards the top, compared to some of these other sectors, especially steel, making up that big purple portion. So, okay, now let's say we do have hydrogen available for power generation. What's the cost at which it would be available? So based on S&P, in 2030, for early markets that are deploying green hydrogen in APAC, the delivered cost would be about $10 per kg. But there are a lot of developments going on for these costs to come down. So as you can see in 2040, we could see a 30% decrease with a delivered cost of $6.8 per kilograms. You can see that this delivered cost is split almost evenly between the cost of green hydrogen production, as well as the storage and transportation costs. So now if you're like me and you're used to seeing fuel pricing figures for gas and liquid fuels, then the dollar per kg figure might not mean much to you. So as a rule of thumb for hydrogen, $1 per kilogram roughly equates to $7.50 per MMBTU. So what this means that in 2040, the pricing that you're seeing is roughly $50 per MMBTU. Now, today, depending on where you are in Southeast Asia, the delivered cost of natural gas or LNG could be around $15, so $15 per MMBTU, which is less than 1/3 of the cost of hydrogen. So I think this just further backs the point that we discussed earlier, that there's definitely a need for government support and grants for these hydrogen projects to be economically viable, even with all these ongoing cost developments. So that was the first point of our hydrogen trilemma. Now let's move on to the midstream infrastructure for hydrogen. Now, hydrogen is a bit tricky because 1, it's not very dense. 2, it's a very small molecule, so it leaks quite easily. And 3, hydrogen is very flammable. So given these constraints, it is still possible to move hydrogen by pipeline, by truck, rail, or by ship. So hydrogen as a gas at room temperature takes quite a lot of space. So it's roughly 3 times more space than natural gas and 300 times more space than diesel. So if you're talking about, let's say, 100 megawatt baseload power demand, you'll roughly need 900 tons of hydrogen per week. So that's a fair bit of hydrogen. And so the question becomes, how can this amount of hydrogen be stored? So if you talk about larger tank sizes, you'll need about 300 units. And if you talk about 45-foot shipping containers, you're talking about over 800 units. So cost is one thing when it comes to the storage, but also this creates a massive logistical and handling challenge. So for this reason, like mentioned before, hydrogen should not be used as a baseload fuel, but rather should be acting as a balancing fuel in a net zero power system. So it's, the picture is not all that bad. While it might seem quite challenging, there are a lot of measures that are being taken today to invest in pipelines and storage of hydrogen. So there are only a few hydrogen pipelines that have reached FID. So what you can see here, again, from Bloomberg New Energy Finance, is by 2030, there could be about 17,200 kilometers of hydrogen pipelines based on announced projects today. Now, for context, in 2019, there were 3 million kilometers of natural gas transmission pipelines, according to the IEA. So there is a pretty big gap that needs to be filled. But as you can see, the pipeline investments here are being driven by Germany, with 27% of those proposed projects coming from there, with quite a significant portion also then coming from the US. Yeah, and so storage is also crucial for hydrogen supply, although progress on the storage front has been a lot slower. So this graph on the right here shows the proposals for underground storage. So this is a really effective way of storing hydrogen in large quantities. And that number that you see is just 0.2% of the global natural gas storage capacity today. So again, a big gap to fill. Although here you can see that about 60% of the global storage capacity is actually being proposed to be built in the US. So the key takeaway here is there are a lot of measures being taken to build hydrogen infrastructure, but it's just critical to remember that hydrogen will act as a balancing fuel, not baseload, and there is still a very long way for the APAC region to go if they want to make hydrogen a reality. So, all right, now jumping to our last piece in the hydrogen trilemma, which is having the technology to be able to run on hydrogen. And this is going to be crucial to make hydrogen-based power generation a reality. The first step, while the industry is ramping up on the supply and infrastructure of the molecule, is to actually be able to blend hydrogen into existing and available fuels. And today, Wärtsilä engines are able to run on a 25% hydrogen blend without any modifications on the engine, and this correlates to approximately a 10% CO2 emission reduction. And a really good example of this is a Wärtsilä engine power plant in Michigan in the US, where we conducted the world's first utility scale and grid connected hydrogen blending test in a reciprocating engine power plant. It was a 55 megawatt engine based power plant. And these blending tests are a great way to test out the technology and lower emissions progressively and steadily. But we don't stop there. The final step to a fully decarbonized system will be a full hydrogen-ready engine power plant. And I'm very happy to say that Wärtsilä has launched the world's first large-scale hydrogen engine power plant, one that has also been certified by TÜV. So there's a lot of progress that's being made on that last point of the hydrogen trilemma. So just to conclude, we are seeing steps being taken in the right direction when it comes to the supply and cost of hydrogen, the infrastructure in terms of storage and transportation, but we will need strong support from government policies, from grants and investments. As you can see, the technology is ready for hydrogen to be used as a balancing fuel. And hopefully by this time next year, we have even more positive developments in that last mile decarbonization that's needed towards a net zero power system in Southeast Asia. Thank you.